Hi everybody, this is your practice problems video for properties of quadrilaterals. So I'm going to start out, we're going to do some classifying. I'll do a couple of problems with parallelograms and rhombuses, and then we'll do a couple with isosceles trapezoids so you can get a good overview, a general idea of what problems with quadrilaterals might look like. Okay, all right, so let's take a look here. So I have this lovely Venn diagram. Okay, and we're essentially going to classify all of our quadrilaterals and put them in the right spot in this Venn diagram. So remember, with Venn diagrams, the bigger the circle, the more general, um, or the more it can encompass. The smaller the circle, or the further inside, like if it's in multiple layers, essentially of circles or of categories, then that means it has to be a little bit more specific, has to have more categories. Okay, so A is my largest circle, which is just this, polygons, which just means shapes. Okay, so A here is polygons. Make that bigger. Hold on. Okay, and then B, so A is like outside, it's anything outside of this circle, right? So that's just any shape. Okay, and that means B would have to be the most general type of four-sided shape, which is a quadrilateral. Okay, all right, and then we have three sets of, or three groups essentially. We have one group that has two items, one group that has one, and then one group that has four. Okay, and so for example, in this group on the right that has two quadrilateral types in it, you have one that's a little bit more general and one that's a little bit more specific. So that makes me think that these are trapezoids, right? Because you have general trapezoids, and then the only other type of specific trapezoid is an isosceles trapezoid, right? Um, the other uh, the other umbrella term would be parallelograms, but there's not enough and not enough circles or spaces inside of circle C for parallelograms to fit there, right? Because if you remember from the notes video, that parallelogram is like this big umbrella and it has lots of shapes underneath it. Okay, so that means C should be a trapezoid and D would be an isosceles trapezoid. Okay, so then if we go over to E, F, G, and H, that has to be that's like our parallelogram umbrella, right? Because you've got lots of things uh, inside the general circle, which is the E circle. So E would be your umbrella, your parallelogram, right? And then we're going to get, like I said, more specific as the circles get smaller, right? So F and G would be like your two slightly more specific types of parallelograms. So rectangles and rhombi, that's the plural for rhombuses. You could switch the order of these here. It doesn't really matter. Okay, and then H, because it has properties of both the rectangle and the rhombus, has to be the square. Okay, and then my very last one is the only one that I have left, which is a kite, which makes sense, right? Because the kite is kind of off in its own world. It doesn't really have a connection to any other type of parallelogram, or any other type of quadrilateral for that matter. Okay. All right, so let's look at some practice problems. So for 2 and 3 here, we're dealing with this rhombus right here. So remember, with a rhombus, we have 4 congruent sides, we have angles that are bisected, and we have 90-degree or perpendicular diagonals. Okay, so 2 says solve for x if AB is 4x plus 18, and the perimeter is 120. Okay, so what that means, remember, in a rhombus, all 4 of these sides are the same. So really, I have 4 4x plus 18s, right? I'm not going to write it on all the sides, but I have 4 of them, right? And remember that for a perimeter, right, you're just adding all of the sides together and setting it equal to the perimeter. So I have 4x plus 18s, and all of that together has to equal 120. Okay, so that's this for number 2, right? That's the equation here for number 2. Okay, so there's a couple of ways that you can solve this. What I think I'm going to do is actually, what you can do is you could distribute the 4 into these parentheses, but what I think I'm going to do actually is divide both sides by 4 so that this will cancel out, just so that I don't have to deal with it anymore. So what I have is 4x plus 18 equals 30, right? So basically what I'm saying is if all 4 sides together are 120, each side has to be 30, right? So now this becomes a simple algebra equation for me to solve. So I have 4x equals 12 and divide by 4. So I end up with x is equal to 3. Okay? All right, then for number 3, we're dealing with the same picture, but they're telling us that, here, let me switch my colors. They're telling us that angle ABD, so ABD is this angle here, is 32 degrees. Okay, and they want us to find all of these missing angles. So remember that all of my angles in the middle are 90 degrees because they're perpendicular. All of the angles are bisected or cut in half by their diagonals, okay? And the angles that are across from each other are congruent, okay? So for angle 1, since angle B here is bisected, angle 1 has to be the same as angle ABD, right? They're congruent, right? Which means that angle 1 is 32 degrees, okay? That also means that angle 4 is 32 degrees, right? Because remember that the angles that are opposite of each other are congruent, okay? And angle B and angle D are opposite each other. So this has to be 32, 32. This one's also 32, okay? So angle 4 is 32 degrees. Okay, 2 is pretty simple because it's one of the angles in the middle. It's perpendicular, right? Perpendicular diagonals for angle 2. So 90 degrees there. Okay, then angle 3 is my last tricky one. All right, if angle 2 is 90 degrees, look, all of these angles are 90 degrees. So now if you can see, I have this small triangle right here inside that I can use the triangle sum theorem to help me find angle 3. So I know that 32 plus 90 plus angle 3 has to equal 180. Okay, so this here is 122 plus angle 3 equals 180. I'm going to subtract 122 from both sides. So I have angle 3 equals 58 degrees. Okay, so 58. Right? Now, another way you could have done that is said, well, okay, I could use my opposite and my supplementary angles going on here, right? So I know that this whole angle, angle B, is 64. So that means that this whole angle A is 180 minus 64, okay, which is, oops, I'm struggling to write here. Okay, oops, hold on. Let me switch back here. So 180 minus 64 is 116. And then if you cut that in half, right, because you have a bisected angle here, then you get 58 for each of these, 58, 58. Okay, which would be the same thing down here, 58, 58. Okay, so a couple different ways you could solve that one. All right. Okay, so let's take a look now at number 4. Okay, so I have a parallelogram, right? And we're going to use the equations that they gave us and do some solving. So they said En is 5y plus 1 and ax is 8y minus 5. Now remember, one of the rules, or the general rule for parallelograms, the thing that you want to remember is you have a lot of opposite things, right? Sides, angles that are equal or congruent. So what I'm going to do is I'm going to set these equal to each other. 5y plus 1 equals 8y minus 5. Okay, then I'm going to solve this for y. So I'm going to do minus 5y minus 5y. Okay, so I end up with 1 equals 3y minus 5. I'm going to add 5 to both sides, plus 5 plus 5. So I have 3y equals 6. And then I'm dividing by 3 on both sides, so you end up with y equals 2. Okay, all right. Okay, and then that second problem there is ET is x plus 1, and then EA, which is this whole thing, is 3x minus 10. Now, this is a little bit trickier. What a lot of people like to do is say, oh, those things just have to be equal, but they're not, right? One of them is just a part of the diagonal, and the other expression is the whole diagonal, okay? So they're not equal, but what we do know is that the diagonal is bisected or cut in half. So if this half, ET, is x plus 1, this half, AT, is also x plus 1, okay? So now what I can do is say, well, all right, so I'm going to take these two things, add them together, and set it equal to 3x minus 10. Remember, that's what we did way at the beginning of the year when we did segment addition? Same idea, okay? So I have 2x plus 1. So 2 times x plus 1 equals 3x minus 10. Sorry, this should say x down here. Oops. Okay, so what I'm going to do is distribute. So I have 2x plus 2 equals 3x minus 10. I'm going to add 10 to both sides. So I have 2x plus 12 equals 3x, and subtract 2x from both sides. So I end up with x equals 12. Okay, your version of the notes will likely have this this fixed. Like I said in a previous video, this is a slightly older version of these notes. Okay, all right, so those are some pretty typical problems for parallelograms, rhombuses, squares, rectangles, that kind of thing, right? Where you've got a lot of things that you're setting equal. You have your bisected ideas, right? Your perpendicular diagonals, all that fun stuff. Okay, so give me a second to clear my screen off, and we're going to do a couple more problems dealing with trapezoids. All right, y'all, so here we are on this second page with practice problems, and we're going to do some practice with trapezoids here, okay? So in both of these problems that I'm going to do, I'm dealing with isosceles trapezoids, okay? Reason I'm doing that is because you have slightly more to work with when you're dealing with an isosceles trapezoid, right? Remember that you have these legs that are congruent. You also have these base angles that are congruent, right, on both the top and the bottom, right? You also have diagonals that are equal, okay? So part A says angle LPN, which is this angle right here, they want to know what that would be congruent to. Well, it's already marked on my diagram. It has to be congruent to PLA because they're both base angles. So angle PLA, those are my congruent base angles, okay? So they said, now they're going to give you some numbers. They say PLA, which is this whole angle right here, is 70 degrees. Okay, so that means LPN, which is this angle across, it's marked in with the 1 mark in purple, that also has to be 70, remember, because the base angles are congruent. Okay, and then PNA is this angle right here. Okay, remember that the leg angles, or the consecutive angles, right, that are connected to the legs are supplementary. So the angle that I'm looking for, plus 70, has to equal 180. So the angle that I'm looking for, if I subtract 70 from 180, is 110. Okay? Right, and then my last one here says, write an equation and solve if AP, which is a diagonal, AP is equal to x, and NL, which is the other diagonal, is 3x minus 8. Remember, in an isosceles trapezoids, the diagonals are equal. So we're going to set those equal to each other. X equals 3x minus 8. Okay, I'm going to do minus 3x on both sides. Since I have x minus 3x, that's negative 2x equals, and then I can't just get rid of this minus sign, I have to bring it down with me, equals negative 8, and I'm going to divide by negative 2 on both sides, so I get that x is equal to 4. Okay, and that's my final answer there. Okay. All right, so let's look at another one that deals with my trapezoids. Okay, and this one has a mid segment in it. Notice that it's called a median here, that you will see that sometimes, but it's the same thing as a mid segment. Okay, right, and this is the median or mid segment of an isosceles trapezoid. So what that means, in any trapezoid, what the mid segment does, which is this EF, right, this the line in the middle there, it cuts the legs in half, okay? But since this is an isosceles trapezoid, since the legs were equal to begin with, that means all of these parts are equal, okay? So that's going to help us solve for y, right? Because I have 2y plus 3 and 6y minus 1. I'm going to have to set those equal to each other, right? So these two right here are equal to each other, okay? To solve for x, I have to do and use my my mid-segment equation, which, if we recall, is I add the bases, okay? So I add the bases, 8x minus 43 plus 10, and cut that in half, and that equals the mid-segment, which is this. So that equals 2x. Okay, all right. So I have this equation here to solve for x. I have another equation to solve for y, which I didn't write, but I kind of told you about. We're going to set these equal to each other. 2y plus 3 equals 6y minus 1. Okay, I want you to use those two equations, see if you can solve for x and y, and then find all of these missing segments. So they want to know what AE, ED, BF, and FC are. Those will all be the same because they're congruent. And once you find x, use that to figure out how long AB and EF are. Okay, so I want you to pause the video now, use these two equations, solve for x and y, find those missing values. Okay, all of these missing values you see on the left here, and then check back with me to see if you were correct. All right, folks, so go ahead and check your answers against mine. So to solve for x, that's over there on the right-hand side of your screen. So just so that I didn't have to deal with the extra, like, divided by 2, the fraction there, I decided to get rid of that first. So I multiplied by 2 on both sides. So I ended up with 8x minus 43 plus 10 equals 4x. And then I combined my like terms. So I have 8x minus 33 equals 4x. And then I subtracted 4x from both sides and added 33 to move that 33 over to the right-hand side and move the 4x to the left-hand side. So you end up with 4x equals 33, divide by 4, and I got x equals 8.25. Then to get a, b, and ef, I just plugged x back into the original expression. So 8 times 8.25 minus 43 is 23, okay, which is right here. Okay, and then 2 times 8.25 is 16.5, okay? Then for the kind of middle portion here, the one that I solved in blue, I set these two equal to each other and solved for y. So I subtracted 2y from both sides, added 1 to both sides. I ended up with 4y equals 4 and got y equals 1. Right? Then all I did is I plugged y back into just one of these expressions. You don't have to do it for both because you'll get the same thing either way. So 2 times 1 plus 3 is 5, which means all of those segments, right, AE, ED, FC, and BF, have to all equal 5 because they're all congruent. Okay. All right, give me a sec to clear my screen off because we've got 2 more questions here. One that's more, it's just a true false, and then one more that's a proof with parallelograms, but not as crazy as you may be thinking, I promise. So I'll see you in just a second. All right, folks, so here we are on our last 2 questions. Now, this first one here is just asking us whether or not these statements are true or false. And in order to kind of help us with that, I'm going to draw this is the parallelogram umbrella, right? So remember, you have parallelograms here, rectangles, rhombuses, and then you have squares down here at the bottom, okay? Right, so remember, anything underneath the umbrella has all the properties of like the upper levels, plus maybe some extra properties of their own, okay? So here, statement A is all squares are rectangles, right? So the way I want to think about this is, do squares have all the properties of rectangles? And they do, right? Because squares are underneath rectangles in the umbrella. So this is a true statement, okay? The other way around is not true, right? If it said all rectangles are squares, that's not necessarily true, right? I can draw a rectangle, not very well drawn, but I can draw a rectangle that's definitely not a square, right? And that's because it's above it, right? In the umbrella, okay? So B says all rhombuses are squares. No, not necessarily true, right? I can definitely draw a rhombus, right? Not very well drawn, but that's a rhombus that's not a square, right? So this is false. Okay, C says all squares are parallelograms. That's true, right? Because squares are underneath parallelograms, right? Right? Squares have all the properties of parallelograms, right? So that just means they're special parallelograms. Okay. D says some squares are kites. If you think back to, let me scroll up. If you think back to our Venn diagram here, remember kites were here, kind of off in their own little land, right? And squares were here, so not really connected at all. Okay. And if you look at the actual definitions of kites, it says that a kite has to have exactly one pair of congruent angles, right? And only the consecutive sides can be like only certain pairs of consecutive sides can be equal or congruent. So this is false. Okay, and then the last here says no rhombuses are trapezoids. I would agree with that. Again, rhombuses and trapezoids are completely separate, right? Trapezoids are not underneath my parallelogram umbrella. So that is true. Okay, all right, so let's take a look here at our last one. Okay, we are given that we have a parallelogram, and we are trying to prove that the 2 triangles that you see are congruent to each other. Okay, there are lots of different ways that you can do this, okay? But our end goal here is to show that we have one of our 4 triangle congruence criteria: SSS, SAS, ASA, or AAS. Okay, that's the goal here, right? So there's lots of different ways that we could set this proof up. Okay, so I'm going to do it a couple of different ways with a couple of different things that'll be marked. Okay, so I'm going to do this one in pink here. All right, so I have my statements here, and then I have my reasons here. Okay, so we're starting with a parallelogram. Okay, so that would be like step one. I have parallelogram. Whoops, hold on. And actually, give me one sec. I need to make this a little bit less thick. Okay, so I have parallelogram PQRS. Okay, and my reason would be given. Okay, because I have a parallelogram, then that means that I have tons of properties that I can mark. So what I'm going to try to do with this first one is I'm going to try to show this works with SSS. Okay, so which means I have to be able to mark my sides as congruent here, all of my sides. So there's one side that I can mark for sure, right, which is this one, PR, is congruent to itself, okay? And then if you remember, the rule with parallelograms is that opposite sides are congruent. So PQ is congruent to RS, and QR is congruent to SP, okay? So now I have all three sides marked. So I can show that this is true by SSS. So step 2 would be PR is congruent to itself. Okay, remember by the reflexive property. Okay, step 3 is my other congruence marks that I have here, and I'm going to put them in one step because they have the same reason. So PQ is congruent to RS, and QR is congruent to SP, okay, and my reason is that opposite sides in a parallelogram are, whoops, hold on, are congruent, okay? So now I have side, side, side. So I can say that those triangles are congruent. PQR is congruent to triangle RSP. Okay, by SSS. Okay, so that's one way, right, that you could prove this. We could also go and prove it with angles. So I'm going to do it one more way, right? So I did SSS, right? And I'm going to do it one more way using ASA, I think. Just so that you can see how this would be done using a couple of different reasons that deal with the angles rather than the sides. Okay, so I'm going to do a second proof here. I'm trying to color code for you all. So I'm going to do a second proof that shows this with ASA. So I'm going to do those and kind of do those marks in green. Okay. So, whoops. All right. Okay. Give me one sec. I need to do some erasing and some setup here, and then I'll be back and we'll do this another way. All right, folks. So like I said, we're going to do this a slightly different way, just because I want to show you how you would write a proof using like some alternate interior angles and some other reasons, right, other than the ones that I have listed here. Okay, so if I wanted to show this was true with ASA, here's what I'm going to do. Okay, I know for sure this is a parallelogram, so I know that angle Q and angle S have to be congruent because they're opposite angles. Okay, I also know if I extend line PQ and line RS and extend this diagonal right here, right? Remember, I have two sets of parallel lines cut by a transversal. So what that means is I have alternate interior angles here that are congruent. So I have this angle, QPR, that has to be congruent to SRP because they're alternate interior, right? And then I have my very last congruence thing would be, if I want this to be ASA, I need to mark this side PQ and this side RS as congruent. Again, and we're going to use the same reason that we used in the SSS, that opposite sides in a parallelogram are congruent. Okay, so let's take all of this and actually write it out. Okay, so step 2 here is angle Q is congruent to angle S. Okay, and my reason is that opposite angles in a parallelogram are congruent. And when you're writing proofs, you can abbreviate the same way that I did here, okay? Because we're just using parallelogram properties. They don't really have names, like the theorems don't have names, or these rules don't really have names, okay? So there's an angle, okay? I have my side, PQ is congruent to RS. Same reason that I used in SSS over here, that opposite sides in a parallelogram are congruent. Okay, and then step 4 is my alternate interior angles. So angle QPR is congruent to angle SRP. Notice that I'm writing them in the correct order, right? So those are congruent because they are alternate interior angles. Okay, so now I have A, S, A in steps 2, 3, and 4. Okay, so now I can say these triangles are congruent. Triangle PQR is congruent to triangle RSP by ASA this time. Okay, so what's neat about this, and what you'll see in a lot of parallelogram proofs and like rectangle proofs, is that you're using a lot of the stuff that you already know, right? And all of your triangle congruence criteria, everything that we've kind of been working on comes together in these quadrilateral proofs, right? All of these ideas of congruent sides and angle relationships with parallel lines and sides that are congruent to themselves, right? All of that stuff comes together with a couple of extra parallelogram rules that allows you to do a lot of cool proofs with parallelograms, right? Another thing I wanted you to see is that there are multiple different methods that you could use to show that those triangles are congruent. I actually could have written a proof for all 4 of these. I could have written an SAS proof and I could have written an AAS proof, and all of them would have been valid, right? So the neat thing about proofs, and kind of why I wanted to show you this, is that it really doesn't matter the path you take as long as the path you take is logical and you end up in the same like spot, basically, okay? Or you end up at the same destination, right? Which is kind of neat, right? So that is all for this video on quadrilateral properties. I hope that it was helpful for you to see some of these examples written out, and I'll see you in the next video. Bye, y'all.